The cosmological principle is the assumption that makes modern cosmology possible, and three structures in the observable universe may violate it. The Huge-Large Quasar group spans 1,240 megaparsecs across its longest axis, approximately 4.04 billion light-years. The giant arc stretches 1 gigaparsec, 3.26 billion light-years. The Big Ring measures 400 megaparsecs in diameter, 1.30 billion light-years. Each of these ultra-large-scale structures exceeds the theoretical upper limit of cosmic homogeneity, the scale beyond which matter distribution should appear statistically uniform. The FLRW metric, the Robertson-Walker spacetime geometry that underlies all standard cosmological calculations, assumes this uniformity exists. If that assumption fails at large enough scales, the equations we use to calculate cosmic expansion, dark energy density, and the age of the universe itself come under pressure. What follows is a forensic examination of the evidence, the structures, the measurements, the counter-arguments, and the implications if any of this is real. By the end of this video, you will understand what the cosmological principle actually claims, how scientists test it, what these ultra-large scale structures are, why some researchers argue they challenge foundational assumptions, and why others argue they are statistical mirages, patterns that emerge from sparse data and aggressive pattern-finding algorithms. You will understand the scale of homogeneity, the concept of the end of greatness, and the methodological disputes that surround every claim in this field. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us begin with what the cosmological principle actually says and what it does not say. The cosmological principle is not a claim that no large structures exist. It is a statistical claim. On sufficiently large scales, the universe's properties are translationally invariant, meaning they do not depend on position, and rotationally invariant, meaning they do not depend on direction. This is called statistical homogeneity and statistical isotropy. The key word is statistical. This is often misunderstood. The cosmological principle does not prohibit individual large structures, and it does not require perfect uniformity. What the cosmological principle requires is that the statistical properties, the averages, variances, correlation functions, become position-independent and direction-independent at large enough scales. A single enormous structure does not automatically violate the cosmological principle. What matters is whether the ensemble properties, the averages, the variances, the correlation functions deviate from what statistical homogeneity predicts. This distinction is critical, and many popular discussions of ultra-large-scale structures skip past it. A billion light-year arc gets presented, and the cosmological principle gets declared dead. The actual scientific debate is more nuanced. The question is not, does this structure exist? The question is, does the existence of this structure, given our survey methods and statistical expectations, indicate a departure from statistical homogeneity? Understanding this requires a deeper examination of what we mean by large scale. In cosmology, scale matters in multiple ways. Angular scale describes how large something appears on the sky. Physical scale describes how large something actually is in space. Redshift affects how we interpret both angular and physical sizes. And there is the distinction between co-moving coordinates, which factor out cosmic expansion, and proper coordinates, which represent actual distances at a given moment. The structures we are discussing are measured in present epoch proper sizes, also called co-moving sizes. This means the numbers represent the distances between objects as they would be measured today, accounting for the expansion of the universe since the light left those objects. The Huge-LQG's 1,240 megaparsec extent is a comoving measurement. The quasars themselves, at redshift 1.27, emitted their light approximately 8.8 billion years ago when the universe was smaller. The physical separation between those quasars at the time of emission was smaller than 1,240 megaparsecs. We conventionally report sizes in present epoch co-moving coordinates to enable comparison across different redshifts. The conversion between redshift and distance requires a cosmological model. The co-moving distance integral is d sub c of z equals c times the integral from 0 to z of dz prime over h of z prime. Here, c is the speed of light, z is redshift, and h of z is the Hubble parameter as a function of redshift. Under flat lambda CDM, the Hubble parameter follows. H of z equals h sub 0 times the square root of omega sub m times 1 plus z cubed plus omega sub lambda. H sub 0 is the present-day Hubble constant, omega sub m is the matter density parameter, and omega sub lambda is the dark energy density parameter. For reference, 1 megaparsec equals approximately 3.26 million light-years, or 3.09 times 10 to the 19th kilometers, or 1.92 times 10 to the 19th miles. When the research literature reports a structure as 1,000 megaparsecs, this corresponds to approximately 3.26 billion light-years, a number easier to conceptualize. The speed of light imposes a fundamental constraint on what structures can mean. Light takes 3.26 billion years to cross a gigaparsec. The universe is approximately 13.8 billion years old. A structure spanning 1 gigaparsec, if it is a gravitationally bound or causally connected entity, must have formed through processes that operated faster than the light crossing time, which essentially requires the structure's coherence to trace back to the very earliest moments, when the scale factors were small enough for causal contact to establish correlations. This is why structures exceeding the homogeneity scale carry cosmological significance. Standard structure formation, the gravitational collapse of initial density perturbations, cannot create coherent overdensities larger than the scale over which matter has had time to gravitationally aggregate. The homogeneity scale represents a natural limit. Above this scale, we expect statistical uniformity because there has not been time for gravitational processes to create larger structures. If structures larger than the homogeneity scale exist, they must either be statistical flukes, chance alignments of unrelated objects, or they must reflect coherence imprinted before the epoch of matter domination, possibly during inflation, or even earlier. The cosmological principle enables the FLRW metric, the Friedmann-Lemaitre-Robertson-Walker spacetime. This metric describes a universe that is homogeneous and isotropic, with a single scale factor A of t that governs how distances change with cosmic time. The line element is ds squared equals minus c squared dt squared plus a of t squared times bracket dr squared over 1 minus kr squared plus r squared d omega squared. In this equation, c is the speed of light, a of t is the scale factor, k is the curvature constant, and d omega squared is the angular element on a sphere. This metric is not a physical discovery. It is an ansatz, a mathematical starting point chosen because it simplifies the equations and appears consistent with observations. If the universe is not statistically homogeneous and isotropic at large scales, this ansatz becomes an approximation at best, a mistake at worst. The Friedmann equations, which govern cosmic expansion, derive from this metric. The equation for the expansion rate is a dot over a squared equals 8pg over 3 times rho minus kc squared over a squared plus lambda c squared over 3. Here, g is Newton's gravitational constant, rho is the mean energy density, lambda is the cosmological constant, and k is the curvature parameter. The critical phrase is mean energy density. In deriving the Friedmann equation, we assume that there exists a meaningful global average density RHO that characterizes the universe. If the universe is not statistically homogeneous, if density varies systematically with position at all scales, the concept of a single global average becomes problematic. The averaging process itself introduces ambiguities that physicists have debated for decades under the name back reaction and averaging problem. This is the theoretical stake. The cosmological principle is not just a philosophical preference for simplicity. It is the structural foundation on which our entire cosmological parameter inference rests. The age of the universe, 13.797 plus or minus 0.023 billion years, according to Planck collaboration fits. The Hubble constant, approximately 67.4 plus or minus 0.5 kilometers per second per megaparsec. The matter density parameter, omega sub m, approximately 0.315. The dark energy density parameter, omega sub lambda, approximately 0.685. All of these numbers come from Fitton models to data while assuming the FLRW framework. If the framework itself is compromised, the numbers inherit that compromise. Now let us examine what homogeneity scale means in practice, how scientists actually test whether the universe becomes uniform at large distances. The operational approach uses counts in spheres and fractal dimension analysis. If you count how many objects, galaxies, quasars, galaxy clusters fall within spheres of increasing radius r, centered on random points, the count n should scale with volume. For a three-dimensional homogeneous distribution, n less than r is proportional to r to the power d sub 2, where d sub 2 is the correlation dimension. If d sub 2 equals 3, the distribution is homogeneous. If d sub 2 falls below 3, the distribution is fractal-like, clumpier than uniform at that scale. The mathematical form is n less than r is proportional to r to the d sub 2 of r. The correlation dimension is computed as d sub 2 of r equals d log n over d log r. Homogeneity corresponds to d sub 2 approaching 3 within some tolerance as r increases. In 2012, Scrimgeour and collaborators analyzed the Wiggle-Z Dark Energy Survey, a spectroscopic survey of emission-line galaxies. They measured the correlation dimension across multiple redshift bins up to Z approximately 0.8. The results showed D sub 2 within 1% of 3 beyond approximately 70 to 81 hours inverse megaparsecs. In units where h equals 0.7, a common approximation based on the Hubble constant, this corresponds to approximately 100 to 116 megaparsecs, or roughly 326 to 378 million light-years. The Wiggle-Z analysis excluded a fractal dimension below D sub 2 equals 2.97 on scales of approximately 80 to 300 H inverse megaparsecs at 99.99% confidence. The Wiggle-Z survey proved particularly valuable for this test because it provides spectroscopic redshifts, precise distance measurements based on emission lines, rather than photometric estimates with larger uncertainties. The survey covered approximately 800 square degrees of sky and included over 200,000 galaxy redshifts across multiple fields. This large statistical sample enables robust measurement of the correlation dimension across a wide range of scales. Earlier work by David Hogg and collaborators in 2004 and 2005 demonstrated cosmic homogeneity using luminous red galaxies from the Sloan Digital Sky Survey at Z approximately 0.3. They showed that n of r, the count of galaxies within radius r, scales as r cubed for r greater than approximately 70 H inverse megaparsecs, with RM's density variations across large regions approximately 7% of the mean. This was among the first direct demonstrations that the universe does approach statistical uniformity at sufficiently large scales. These measurements establish the empirical homogeneity transition. Below approximately 100 megaparsecs, the universe is demonstrably clumpy, filaments, walls, voids, clusters. The cosmic web, that intricate network of galaxy filaments surrounding vast empty regions, dominates the structure at these scales. Above approximately 100 megaparsecs, the correlation dimension approaches 3. Meaning the distribution becomes statistically consistent with uniformity. The variance shrinks. The fluctuations average out. This is the empirical homogeneity transition. The transition is sometimes called the end of greatness, a phrase from a 1996 review that described the scale where survey volumes become fair samples rather than being dominated by individual, massive structures. A theoretical upper limit also exists. In 2010, Yadav, Bagla and Kandai estimated, under idealized lambda CDM assumptions, that the homogeneity scale should have an upper bound near 260 H inverse megaparsecs. In units with H equals 0.7, this is approximately 370 megaparsecs, or about 1.21 billion light-years. Structures larger than this should not exist as coherent overdensities in standard cosmology. The theoretical reasoning follows this logic. In lambda CDM, initial density perturbations are nearly scale invariant, similar amplitude at all scales when extrapolated to early times. These perturbations grow through gravitational instability, but the growth is limited by cosmic time. On scales larger than the horizon at matter radiation equality, perturbations have had less time to grow. The homogeneity scale represents the largest scale at which gravitational aggregation can create significant overdensities within the age of the universe. Perturbations on scales exceeding the homogeneity upper limit should remain small, consistent with statistical homogeneity. If we observe structures on these scales, either the structures are not coherent overdensities, they are chance alignments of unrelated objects, or something in the early universe created correlations on scales larger than standard inflation predicts. This is the number that gives the ultra-large scale structure claims their significance. If a structure exceeds 370 megaparsecs, if it is larger than the theoretical homogeneity upper limit, it represents a potential tension with lambda CDM, not proof of violation. Tension. The distinction matters. Let us now examine the three structures that have generated the most attention. The huge large quasar group, the giant arc, and the big ring. The huge large quasar group, often abbreviated Huge-LQG, was reported in 2013 by Roger Close and collaborators. The structure was identified in the Sloan Digital Sky Survey Data Release 7 Quasar Catalog, DR7QSO, using a hierarchical clustering algorithm with a linkage scale of 100 megaparsecs. The Sloan Digital Sky Survey, operating from Apache Point Observatory in New Mexico since approximately 2000, has provided the foundational datasets for much of modern extragalactic astronomy. The 2.5-meter telescope uses a wide-field camera and multi-fiber spectrograph to image and obtain spectra for millions of objects. DR7, released in 2009, included approximately 120,000 quasars with spectroscopic conformations, each one a supermassive black hole at the center of a distant galaxy, accreting matter and outshining its host by factors of hundreds to thousands. The Huge-LQG analysis used a single linkage hierarchical clustering algorithm, a method that connects objects into groups if they lie within a specified linking distance of each other. This is also called a friends of friends algorithm. Two quasars are friends if they are closer than the linking length. Friends of friends connect into the same group. The process continues until all connections are made. The choice of linking length is consequential. Set it too small and you fragment real associations into multiple pieces. Set it too large and you connect unrelated objects into artificial superstructures. The Huge-LQG analysis used 100 megaparsecs, approximately 326 million light-years. The reported measurements are as follows. Membership 73 quasars. Mean redshift Z approximately 1.27. Characteristic size computed using the convex hull of member spheres method, or CHMS, approximately 495 megaparsecs, corresponding to roughly 1.61 billion light-years or 1.52 times 10 to the 19th miles. Principal axis from the inertia tensor, approximately 1,240 megaparsecs by 640 megaparsecs by 370 megaparsecs. The longest dimension, 1,240 megaparsecs, corresponds to approximately 4.04 billion light-years or 3.83 times 10 to the 19th kilometers or 2.38 times 10 to the 19th miles. The CHMS method deserves explanation. It constructs a convex hull, the smallest convex shape that contains all the member quasars, and then calculates the volume of that hull. The characteristic size is the cube root of this volume, providing a single number that characterizes the overall extent of the structure. Even though the structure is elongated and irregular. The inertia tensor method provides more detail. It treats each quasar as a point mass and computes the moment of inertia tensor of the distribution. The eigenvalues of this tensor give the principal moments, and their ratios indicate the shape. For the Huge-LQG, the three principal axes, 1240 by 640 by 370 megaparsecs, indicate a highly elongated, roughly prolate structure. Think about that number. Let it settle. 1240 megaparsecs. A light beam traveling at 299,792 kilometers per second, 186,282 miles per second, would take 4.04 billion years to cross this structure. The age of the universe under lambda CDM is approximately 13.8 billion years. The light-crossing time of the Huge-LQG is nearly 30% of cosmic history. Let me make this more concrete with some comparative scales. The Milky Way galaxy spans approximately 100,000 light-years in diameter, about 30 kiloparsecs. The Huge-LQG is approximately 40 million times larger. If you shrank the Milky Way to the size of a coin, say 25 millimeters, the Huge-LQG would stretch approximately 1,000 kilometers across, roughly the distance from London to Rome. The distance to the Andromeda Galaxy, our nearest large galactic neighbor, is approximately 2.5 million light-years, or about 0.77 megaparsecs. The Huge-LQG is approximately 1,600 times this distance. If Andromeda were an arm's length away, 70 centimeters, the Huge-LQG would lie approximately 1.1 kilometers distant. At 0.1 c, 10% of the speed of light, a velocity no spacecraft has approached, but which serves as a useful benchmark, crossing the Huge-LQG would take approximately 40.4 billion years. This exceeds the current age of the universe by a factor of 3. No causal process operating after the Big Bang could create coherence across such a distance unless that coherence was imprinted at the very earliest moments during or before inflation. At commercial aircraft speed, approximately 1,000 kilometers per hour, crossing 1 megaparsec would take approximately 3.5 trillion years. Crossing the Huge-LQG would take approximately 4.3 quadrillion years, about 300,000 times the current age of the universe. These numbers are not meant to be dramatic. They are meant to convey the disconnect between human scales and cosmic scales. We speak of structures as if they were objects we could perceive, navigate, comprehend. A billion light-year structure is not an object in any familiar sense. It is a statistical pattern in the positions of 73 quasars, each itself a supermassive black hole billions of light-years away, emitting light we will never see again. The reported statistical departure from random expectations using the CHMS method was 3.81 sigma. The estimated quasar overdensity was delta sub Q approximately 0.40. The authors argued that the characteristic size, and especially the longest dimension, exceed the homogeneity upper limit, and that the Huge-LQG represents a challenge to the cosmological principle. Counter-arguments came quickly. In 2013, Seshadri Nadatha published a critique arguing that a single large structure does not automatically falsify statistical homogeneity. Homogeneity is an ensemble property. It concerns the statistics of many regions, not the existence of one unusual region. This is a fundamental point that is often misunderstood in popular discussions. Consider an analogy. If you flip a fair coin 100 times, you expect approximately 50 heads. Getting 60 heads does not prove the coin is biased. Random processes produce fluctuations. The question is whether the fluctuation exceeds what random processes predict. The same logic applies to cosmology. Even in a perfectly homogeneous universe, you expect rare, large fluctuations. The question is not whether a large structure exists, but whether structures of that size appear more often than statistical homogeneity predicts. Nadatha applied the same clustering algorithm to Poisson simulations, random point distributions with no physical clustering, and found that clusters as large as or larger than the Huge-LQG appeared in approximately 8.5% of simulations. 8.5%, not negligible. If similar-sized clusters appear in nearly 1 in 10 random catalogues, the Huge-LQG may be a statistical artifact of the clustering algorithm rather than evidence of physical structure. The key insight is that the clustering algorithm itself can create apparent structures from random noise. When you connect all objects within 100 megaparsecs of each other, sparse random points can percolate into large connected components. This is not a failure of the algorithm. It is doing exactly what it is designed to do. It means that large groups in sparse catalogues require careful null testing to determine whether they exceed random expectations. Nadatha also tested homogeneity directly on the DR7QSO catalogue using counts-in-spheres methods. The result, the quasar distribution is consistent with homogeneity above approximately 130 H inverse megaparsecs, roughly 185 megaparsecs. The Huge-LQG, by this analysis, does not indicate homogeneity violation. This is a direct test of the cosmological principle using the same data. The counts-in-spheres method does not depend on clustering algorithms or linking lengths. It simply asks, how does the count scale with radius? And the answer is, consistently with d sub 2 equals 3. With homogeneity above the transition scale. In 2015, Changbom Park and collaborators pushed further. They analyzed the size and richness distributions of the largest quasar groups found with a linking length of 70 H inverse megaparsecs. Their finding, the distributions were statistically equivalent to random catalogues with the same density and sky footprint. The Huge-LQG-like structures could arise with high probability without any physical clustering. Park recommended using smaller linking lengths below 50 hours inverse megaparsecs to avoid chance associations dominating the results. Parkes' analysis proved particularly important because it systematically varied the linking length. At 70 hours inverse megaparsecs, slightly smaller than the 100 megaparsec scale used for the Huge-LQG, the largest groups were already indistinguishable from random. This suggests the Huge-LQG owes its size to the specific linking length chosen, not to an underlying physical overdensity. In 2024, Fuji analyzed whether large quasar groups trace statistically significant high-density regions when tested against more robust DR16 large-scale structure quasar samples. The conclusion: some LQG catalogues are likely dominated by chance associations and are not suitable for cosmological inference. This is the methodological core of the dispute. The structure depends on how you define a structure. The linking length, the maximum separation at which two quasars are counted as neighbors and merged into the same group, is a free parameter. Set it too large, and you link unrelated objects into artificial agglomerations. Set it too small, and you miss real associations. There is no uniquely correct choice. Different choices produce different results. Let me elaborate on this point because it is essential for understanding the entire controversy. Imagine scattering 73 points randomly in a three-dimensional volume. You want to determine whether they form a coherent structure or are just randomly distributed. The Friends of Friends algorithm works by connecting points that lie within some linking distance L of each other. Points connected directly or through chains of connections form a group. The algorithm will always find groups if L is large enough. This is mathematically inevitable. Even in a perfectly random distribution, some pairs of points will be close to each other by chance. Connect those pairs and you form groups. Make L larger and the groups grow. At some L, all points merge into one giant connected component. The question is not whether groups exist. They always do for large enough L. The question is whether the groups are statistically significant, whether they are larger, richer, or more clustered than what random processes predict. This requires null testing. You generate many random catalogs with the same density and geometry as the real data. You run the same algorithm on each random catalog. You measure the size and richness distributions of the resulting groups. Then you compare the real groups to the random groups. If the real groups are vastly larger or more common than the random groups, you have evidence for physical clustering. If they are comparable, you have evidence that the structures are pattern-finding artifacts. The Huge-LQG was found with a 100 megaparsec linking length. Critics argue this is too large, that at these separations, chance alignments masquerade as physical structures. Defenders argue the CHMS significance test accounts for this. The debate continues. I return to this point often, not for comfort, for clarity. The most unsettling outcome is not new physics confirmed or statistical artifact debunked. The most unsettling outcome is indeterminacy, multiple hypotheses fitting partial data with no decisive test to separate them. Now let us examine the giant arc. The giant arc was reported in 2022 by Alexia Lopez, Roger Klaus, and Gerard Williger. Unlike the Huge-LQG, which was found in a quasar catalogue, the giant arc was identified using intervening Mg2 absorbers in background quasar spectra. This is a fundamentally different tracer methodology, and it requires explanation. When astronomers observe a quasar, a supermassive black hole actively accreting matter and producing intense radiation, the light from that quasar travels billions of light-years to reach us. Along the way, it passes through intervening galaxies and their surrounding halos. Gas in those halos absorbs certain wavelengths, leaving characteristic dips in the quasar's spectrum. Mg2 absorbers are a specific type of absorption feature. When light from a distant quasar passes through the halo of a foreground galaxy, magnesium atoms in that halo absorb photons at specific wavelengths corresponding to the magnesium-2 transition, a doublet at 2796 and 2803 angstroms in the rest frame. Because the foreground galaxy is at a different redshift than the background quasar, these absorption features appear at shifted wavelengths, allowing us to determine the redshift of the absorbing gas. By cataloguing Mg2 absorbers across many quasar spectra, researchers can map the locations of foreground galaxies without observing those galaxies directly. Each absorber indicates the presence of foreground gas associated with a galaxy halo at a specific redshift and sky position. The advantage of this method is that it provides spectroscopic redshifts, precise distances for the foreground structure. The disadvantage is sparsity. Mg2 absorbers are far less numerous than galaxies or quasars. The typical sky density is low, making pattern finding more susceptible to chance alignments. The giant arc was found at redshift Z approximately 0.8 using Mg2 absorber catalogues compiled by Zhu and Menard from SDSS spectra. The tracer is sparse, far fewer absorbers than galaxies or quasars, but it is spectroscopic, meaning redshifts are precise rather than photometric estimates. The reported measurements, the giant arc spans approximately 1 gigaparsec, 1000 megaparsecs in present epoch proper size. This corresponds to approximately 3.26 billion light-years, or 3.09 times 10 to the 19th miles. The light-crossing time at the speed of light is approximately 3.26 billion years. The statistical significance was method-dependent. Approximately 4.5 sigma using single-linkage hierarchical clustering, approximately 3.0 sigma using the Cusick-Edwards test, and approximately 4.8 sigma using power spectrum analysis. The estimated overdensity was delta RHO over RHO, approximately 1.3 plus or minus 0.3. The density contrast, delta, is a fundamental quantity in cosmological structure studies. It is defined as delta equals rho minus rho bar over rho bar. Here, rho is the local density and rho bar is the mean cosmic density. A delta of 0 means the region has average density. A positive delta means overdensity, more matter than average. A negative delta means underdensity, less matter than average. An overdensity of delta equals 1.3 means the region contains approximately 2.3 times the average cosmic density. This is substantial, comparable to the overdensities associated with galaxy clusters, though on a vastly larger scale. Interpreting overdensity from sparse traces requires caution. The MG2 absorbers do not directly measure mass density. They measure the presence of magnesium-enriched gas in galaxy halos. The assumption is that more absorbers indicate more galaxies, which indicate more mass. Each step involves modeling assumptions and potential biases. The overdensity estimate depends on the assumed background, what you compare the local density to. If the background is not representative of the true cosmic mean, the overdensity estimate is biased. In a sparse tracer sample with potential selection effects, establishing the true background is challenging. 1 gigaparsec. Far above the 370 megaparsec theoretical homogeneity upper limit. If this is a real, coherent structure, a physical overdensity rather than a chance alignment of sparse tracers, it represents a significant tension with the cosmological principle. The paper itself uses cautious language. Challenge is not the same as contradict. The authors discuss mitigation of post hoc significance concerns, the look elsewhere effect. When you search for patterns across a large sky area and many redshift slices, you increase the probability of finding something that looks significant by chance. The question is whether the search strategy adequately controls for this. A 2025 preprint explicitly tests whether the giant arc is a sparse MG2 pattern consistent with standard large-scale homogeneity. The title frames the question directly: filament or figment? The authors treat the contradiction claim as something requiring verification, not as established fact. This is the state of the debate. The giant arc exists as a pattern in MG2 absorber data. Whether it represents a physical overdensity exceeding homogeneity limits, or whether it is a statistical fluctuation in sparse tracer data, remains contested. Now let us examine the Big Ring. The Big Ring was reported in 2024 by Alexia Lopez and collaborators, the same team behind the giant arc discovery. The Big Ring was found near the giant arc at the same redshift of Z, approximately 0.8, with the sky separation of approximately 12 degrees. The Big Ring was identified using MG2 absorber catalogs restricted to SDSSDR16Q quasars. The reported measurements: diameter approximately 400 megaparsecs, 1.30 billion light-years, or 1.23 times 10 to the 19th miles. The light crossing time at the speed of light is approximately 1.30 billion years. The statistical departure from random expectations using the CHMS method for the annulus plus inner absorbers reached up to 5.2 sigma as reported. The authors introduced the term ultra-large scale structure, ULSS, specifically for structures exceeding the 370 megaparsec upper limit to the homogeneity scale cited in cosmological principle discussions. The Big Ring was classified in this context. The paper explicitly discusses look elsewhere concerns. The authors argue that their search strategy, focusing primarily on the same field and redshift slice where the giant arc was found, limits the effective number of independent trials. Whether this adequately addresses the concern is a judgment call that different analysts may assess differently. The Big Ring paper also mentions a speculative origin hypothesis: cosmic strings. Cosmic strings are one-dimensional topological defects that could form during early universe symmetry-breaking phase transitions. If cosmic strings exist, they could seed distinctive linear or ring-like features through gravitational effects. The paper presents this as an example of a possible non-standard explanation, not as a conclusion. Cosmic strings are constrained but not ruled out. CMB observations and gravitational lensing searches impose limits on the contribution of cosmic strings to structure formation. No definitive detection has been made. The cosmic string hypothesis for the Big Ring is speculative, a possibility mentioned for completeness, not a preferred explanation. Before I continue, consider what this means. Take a moment. We have three claimed structures: the Huge-LQG at 1,240 megaparsecs, the Giant Arc at 1,000 megaparsecs, and the Big Ring at 400 megaparsecs. All exceed the theoretical homogeneity upper limit of approximately 370 megaparsecs. All have been challenged on methodological grounds, linking length sensitivity, sparse tracer statistics, look elsewhere effects, the difference between pattern finding and physical clustering. The debate is not about whether patterns exist in the data. Patterns clearly exist. The debate is about what those patterns mean, whether they reflect physical overdensities that challenge cosmological assumptions, or whether they are artifacts of how we search for patterns in inherently noisy, sparse data sets. This is the forensic uncertainty at the heart of the field. Not certainty in either direction. Uncertainty. Let us now turn to a different kind of evidence for cosmological principle tension: cosmic anisotropy signals. If the universe is statistically isotropic, the same in all directions, then certain observables should show no preferred direction. If they do show preferred directions, isotropy is violated. This is a conceptually distinct test from homogeneity. Homogeneity concerns whether properties vary with position. Isotropy concerns whether properties vary with direction. A universe can be homogeneous but anisotropic, the same everywhere but different in different directions. Or it can be isotropic but inhomogeneous, the same in all directions from any point but varying with position. The cosmological principle requires both statistical homogeneity and statistical isotropy together. The central test is the cosmic dipole. The cosmic microwave background exhibits a dipole pattern. One side of the sky is slightly hotter, the other slightly cooler. The temperature difference is approximately 3.4 millikelvin peak to peak, on a background of 2.725 Kelvin, about 1 part in 800. Under standard cosmology, this dipole is purely kinematic. It reflects our motion through the CMB rest frame at approximately 370 kilometers per second toward the constellation Leo. As we move through the CMB, photons arriving from the direction of motion are blue-shifted to higher energies, appearing hotter. Photons arriving from behind are shifted to lower energies, appearing cooler. This is the Doppler effect applied to the cosmic thermal background. The CMB dipole is not an intrinsic property of the universe. It is an artifact of our velocity. Every observer moving through the CMB sees a dipole corresponding to their velocity. If the universe is isotropic, the same dipole, with the same amplitude and direction, should appear when we count matter tracers like galaxies, quasars, or radio sources. The kinematic motion that Doppler shifts the CMB should also aberrate and modulate the apparent density of matter sources on the sky. Sources in the direction of motion appear slightly more numerous through aberration concentrating them, and slightly brighter through Doppler boosting. Sources opposite our motion appear slightly less numerous and dimmer. The predicted effect is calculable from special relativity. The matter dipole amplitude should be approximately 2 times v over c times alpha, where v is our velocity, c is the speed of light, and alpha is a factor related to the source count slope with flux. For typical source populations, the predicted dipole amplitude corresponds to approximately twice the CMB dipole amplitude. Observations show something unexpected. A widely cited 2021 analysis by Nathan Sechrest and collaborators used 1.36 million quasars from the CAT-WISE 2020 catalogue based on WISE infrared all-sky observations. WISE, the Wide Field Infrared Survey Explorer, was launched by NASA in December 2009 and surveyed the entire sky at infrared wavelengths. The all-sky coverage is essential. Any dipole measurement requires observations across the full celestial sphere, not just patches. The CAT-WISE 2020 catalogue represents a reprocessing of WISE data with improved astrometry and photometry. The 1.36 million quasars used in the dipole analysis were selected based on infrared colors and cross-matching with other catalogues. Quasars are useful for dipole measurements because they are distant and approximately uniformly distributed. They should trace the cosmic matter distribution on the largest scales. The quasar number count dipole was measured. The analysis counted how many quasars appear in different directions on the sky, modeled the expected kinematic dipole from our motion through the CMB rest frame, and compared. The direction was consistent with the CMB dipole, both point roughly toward Leo. The amplitude was more than twice the kinematic expectation. The reported p-value was approximately 5 × 10⁻⁷, corresponding to roughly 4.9 sigma one-sided for rejecting a purely kinematic interpretation. To understand what this significance means, under the null hypothesis that the matter dipole is purely kinematic, the probability of observing a dipole amplitude as large as or larger than measured is approximately 1 in 2 million. This is a low probability. Low probability is not zero probability. The 5 sigma threshold, sometimes called the discovery threshold in particle physics, corresponds to a probability of approximately 3 × 10⁻⁷. The cosmic dipole anomaly at 4.9 sigma in the original analysis approaches but does not quite reach this threshold. The 5 sigma threshold assumes no systematic uncertainties beyond those modeled. If systematics are underestimated, the true significance is lower. This is why subsequent reanalyses with more sophisticated systematic modeling have reported reduced significance, 3.3 to 3.6 sigma rather than 4.9 sigma. A significance of 3.3 sigma corresponds to a probability of approximately 0.05%, 1 in 2000. Still notable, not decisive. Scientific conclusions require either higher significance or independent confirmation. This is called the Cosmic Dipole anomaly. the matter dipole appears too large to be explained by our motion alone. If confirmed, it would indicate that the matter distribution itself has an intrinsic dipole, a genuine directional asymmetry, which would violate statistical isotropy. Subsequent analyses have both strengthened and complicated this finding. In 2023, Dam and collaborators performed a Bayesian analysis and reported a dipole amplitude approximately 2.7 times the kinematic expectation, with a reported significance of approximately 5.7 sigma. A 2025 reassessment using simulations that include clustering dipole, shot noise, and mask/geometry effects reduced the significance to approximately 3.3 to 3.6 sigma, depending on modeling assumptions. The anomaly is not eliminated. 3.3 sigma is still notable, but the original claims of 5 sigma may have been inflated by incomplete systematic modeling. A 2025 colloquium review frames the cosmic dipole anomaly as a major challenge for perturbed FLRW cosmology if systematics cannot account for it. The review explicitly states that with modern near-all-sky radio and quasar catalogues, the matter dipole appears aligned in direction with the CMB dipole but anomalously larger in amplitude, and states the discrepancy exceeds 5 sigma in some analyses. The Planck collaboration's isotropy and statistics analysis, their final 2018 results, provides additional context. Planck reports that CMB temperature anisotropy statistics are broadly consistent with Gaussian lambda CDM predictions, while also confirming several large-angle anomalies, including the hemispherical power asymmetry and the alignment of low multipoles. Planck does not claim unambiguous anomaly detections in polarization at large scales, noting that residual systematics can limit some tests. Let me explain these anomalies more precisely because they are often misunderstood. The hemispherical power asymmetry is a measured difference in the variance of CMB temperature fluctuations between two hemispheres of the sky. If you divide the CMB into a northern and southern hemisphere, with the division plane chosen to maximize the asymmetry, the variance differs by approximately 6 to 7%. This is unexpected under statistical isotropy, where both hemispheres should have the same statistical properties. The reported significance depends on how you account for the choice of division plane. If you compute the probability of finding such an asymmetry in a randomly placed hemisphere, it is low, approximately 1% or less. You chose the plane to maximize the asymmetry. This inflates the apparent significance, the look elsewhere effect. Accounting for this, the anomaly becomes less dramatic, though still present. The low multipole alignment refers to the unexpected alignment of the quadrupole and octopole, the two largest scale patterns in the CMB after the dipole. In a statistically isotropic universe, these patterns should be randomly oriented. Observations show they are aligned with each other and with the direction of the CMB dipole. The alignment is sometimes called the axis of evil in popular discussions. Again, significance assessment is tricky. The alignment exists. Its interpretation is debated. Some researchers argue it is a statistical fluke, unlikely but not impossible in a single realization of a random field. Others argue it hints at new physics, a preferred direction imprinted by some early universe process. The Planck analysis takes a cautious position. The anomalies are real in the sense that they are measured in the data. Planck does not claim they constitute evidence for new physics. The position is, these features are unusual under lambda CDM, but not so unusual as to rule out statistical fluctuation. The CMB anomalies are a separate issue from the matter dipole, but they share a common thread: hints of preferred directions or unexpected alignments that challenge perfect isotropy. Independent analyses continue to report preferred axis-like effects in Planck maps using alternative statistics, claiming 98 to 99% confidence for a preferred axis. Coordinate conventions and statistic choices vary across papers, making direct comparisons difficult. Supernova anisotropy analyses add another layer. Some analyses of the Pantheon plus supernova sample report anisotropy signals at the few sigma level in fitted cosmological parameters, for example, directional dependence in the deceleration parameter Q sub 0 or the Hubble constant H sub 0. These analyses also explicitly assess that such signals can arise from sample limitations and do not constitute robust evidence of isotropy failure. A 2026 MNRAS analysis finds that dipoles inferred from local distance tracers can be absorbed by more general local flow modeling or systematics, yielding results consistent with standard expectations rather than genuine anisotropic expansion. What would you conclude from this evidence? The cosmic dipole anomaly is real in the sense that the measurements exist and the discrepancy has been reported by multiple independent groups. Whether the anomaly reflects genuine cosmological anisotropy, uncontrolled systematics in catalog construction, or inadequate modeling of local structure effects remains actively debated. This brings us to local non-averageness, the possibility that our location in the universe is not typical, and that local structure biases our cosmological inferences. The cosmological principle assumes that any sufficiently large region of the universe is representative of the whole. This is sometimes called the fair sample assumption. If we observe a large enough volume, we should see average cosmic properties. What if we do not live in an average region? What if local structure within a few hundred megaparsecs deviates significantly from the cosmic mean? In that case, local measurements might not reflect global properties. We would be inferring cosmic parameters from an unrepresentative sample. The KBC Void is the most discussed example of potential local non-averageness. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie measured K-band luminosity density versus redshift and distance using UKIDSS and 2MASS photometry combined with multiple redshift surveys. They analyzed the range 0.01 less than Z less than 0.2, corresponding to distances of approximately 50 to 800 megaparsecs. K-band luminosity, infrared light at approximately 2.2 micrometers wavelength, serves as a good tracer of stellar mass. Unlike optical light, which is dominated by young hot stars, infrared light comes predominantly from older, cooler stars that constitute most of a galaxy's mass. If you measure the total K-band light in a volume, you are approximately measuring the total stellar mass in that volume. And if luminosity traces mass, if more stellar mass means more total matter, then K-band luminosity density traces matter density. Their finding, beyond Z, approximately 0.07, the K-band luminosity density rises to approximately 1.5 times the local value at Z greater than 0.1. If luminosity traces mass, a reasonable but not perfect assumption, this suggests the local region is underdense relative to the cosmic mean. The implied underdensity scale is approximately 300 megaparsecs. The estimated true underdensity, after correcting for void-induced outflows that distort redshift distance mapping, is approximately 20% below the global mean out to approximately 300 megaparsecs. 300 megaparsecs is approximately 1 billion light-years, a substantial fraction of the observable universe's radius. An underdensity of 20% over this scale is cosmologically significant. This is the KBC Void hypothesis. We may be located in a large local underdensity, a void hundreds of megaparsecs across, and this local structure may bias cosmological measurements. Why does this matter? Consider the Hubble-Lemaitre law, the relationship between recession velocity and distance at low redshift. V equals h sub 0 times d. H sub 0 is the Hubble constant. If we measure h sub 0 locally using supernovae, Cepheid variables, or other distance indicators within a few hundred megaparsecs, and if our local region is underdense, the measured h sub 0 will differ from the global value. This is one proposed explanation for the Hubble tension. The discrepancy between the local measurement of h sub 0, approximately 73 kilometers per second per megaparsec from the SH0ES team, and the CMB inferred value, approximately 67.4 kilometers per second per megaparsec from Planck, assuming lambda CDM. If we live in an underdense region, local expansion could be faster than global expansion, inflating the local h sub 0 measurement. Some analyses argue the KBC void amplitude could ease the Hubble tension. Others argue local structure cannot fully account for the discrepancy. The debate depends on density field reconstructions, selection effects, and velocity modeling, all of which carry uncertainties. A 2025 MNRAS synthesis describes the KBC void as an underdense region on a scale of approximately 300 megaparsecs and summarizes analyses placing its true underdensity around 20%. The synthesis discusses baryon acoustic oscillation tests and void hypotheses, treating the local underdensity as a factor that must be accounted for in precision cosmology. The KBC void does not directly relate to the ultra-large-scale structures like the Huge-LQG or giant arc. It shares a conceptual thread: the possibility that our assumptions about cosmic averageness, that our location is typical, that local measurements reflect global properties, may be incorrect. This is the part that stays with me. Not because it is exciting, because it is heavy. We build our cosmological model on the assumption that the universe is statistically homogeneous and isotropic. We derive equations, we fit parameters, we declare precision results, the age of the universe known to 0.17%, the matter density known to 2%. If the foundational assumption is compromised, if we live in a large void, if there are gigaparsec scale structures, if there is a matter dipole inconsistent with kinematics, then the precision is illusory. we have precisely measured the wrong thing. This is not a claim that lambda CDM is wrong. It is a recognition that the framework rests on assumptions that remain under test. The assumptions have survived many tests. They have not survived all tests without anomalies. Let me now address the counter-narrative more systematically, the mainstream defense of the cosmological principle against these challenges. The dominant view in cosmology is that the cosmological principle remains valid as a statistical statement, and that the reported ultra-large-scale structures and anisotropy signals are either artifacts of methodology, expected rare fluctuations within lambda CDM, or incompletely controlled systematics. The first defense is definitional. Statistical homogeneity concerns ensemble properties, averages over many regions, variance across volumes, correlation functions. A single unusual structure, even a very large one, does not violate statistical homogeneity unless it indicates that the ensemble statistics deviate from predictions. The existence of the Huge-LQG, by this argument, is like rolling a 12-sided die and getting a 12. Unlikely on any single roll. Not evidence the die is loaded unless you see too many 12s. Nadathar's analysis operationalizes this argument. Even if the Huge-LQG is the largest structure in the observable universe, similar-sized structures appear in 8.5% of random Poisson simulations. That is not too many. That is consistent with statistical expectation. The second defense is methodological. Structure is an output of algorithms, not a self-evident feature of data. The linking length in friends of friends clustering, the significance threshold in minimal spanning tree analysis, the volume estimator in CHMS, all of these are choices. Different choices produce different results. The Huge-LQG at 100 megaparsec linking length becomes something else or nothing at 50 megaparsec linking length. Park's analysis demonstrates this explicitly. At 70 hours inverse megaparsec linking length, the largest DR7 QSO groups are statistically indistinguishable from random catalogues. Reduce the linking length and the apparently significant structures dissolve. The third defense is tracer-specific. Quasars and MG2 absorbers are sparse tracers. The mean nearest neighbor distance between quasars in DR7 QSO is large enough that percolation-like linking becomes likely at moderate linking lengths. Sparse tracers amplify pattern-finding artifacts. Fuji's 2024 analysis finds that many LQGs do not trace statistically significant high-density regions when tested against more robust DR16 samples. The LQG catalogues by this analysis are dominated by chance associations. The fourth defense is statistical. The look elsewhere effect, the inflation of significance when you search across many parameters and report only the most extreme result, is a known pitfall in anomaly searches. The giant arc and big ring were found by searching across sky positions and redshift slices. How many such searches were performed before something significant was found? The papers attempt to address this, but the adequacy of the correction is a judgment call. The fifth defense is cosmological. The CMB, which probes the universe at Z approximately 1090, when it was only 380,000 years old, is extraordinarily uniform. Temperature fluctuations are approximately 1 part in 100,000 after removing the kinematic dipole. This uniformity is direct evidence for early universe homogeneity. If the universe were fundamentally inhomogeneous, we would expect to see it in the CMB. The Planck final parameter analysis reports consistency of CMB data with base lambda CDM across temperature, polarization, and lensing datasets. The cosmological parameters are internally consistent. The framework works. The sixth defense is observational convergence. Multiple independent probes, CMB, baryon acoustic oscillations, Type 1a supernovae, galaxy clustering, weak lensing, produce consistent cosmological parameters under lambda CDM. This convergence is difficult to explain if the framework is fundamentally wrong. It is much easier to explain if the framework is basically correct and the anomalies are statistical flukes or systematic errors. This is the mainstream position. Not there are no anomalies. The anomalies exist. The position is the anomalies do not yet constitute decisive evidence against the cosmological principle, and the null hypothesis, lambda CDM plus statistical fluctuations plus imperfect systematics control, remains viable. The mainstream position is also not case closed. The debates continue. New data arrives. The arguments develop. Let me now discuss the current observational frontiers, the missions and surveys that will provide better data for testing these claims. The history of this field is a history of increasing data quality. Each generation of surveys provides more objects, better coverage, more precise measurements. And with each improvement, some claimed structures have been confirmed while others have dissolved. The Sloan Digital Sky Survey has been operating since approximately 2000, providing imaging and spectroscopy for galaxies and quasars across multiple data releases. The 2.5-meter telescope at Apache Point Observatory in New Mexico has imaged approximately 1/3 of the sky in 5 optical bands and obtained spectra for millions of objects. The quasar catalogues DR7, DR12, DR16Q underlie most of the LQG and MG2 absorber structure claims. SDSS was foundational but is now being superseded. The statistical power of newer surveys dwarfs what was available when the Huge-LQG was discovered. The Dark Energy Spectroscopic Instrument, DESI, began observations in May 2021 and released Data Release 1 covering observations through June 2022. DESI-DR1 includes 18.7 million spectra, a massive increase in statistical power over SDSS. The instrument uses 5,000 robotic fiber positioners on the 4-meter Mayol telescope at Kitt Peak, Arizona, enabling simultaneous spectroscopy of thousands of targets. DSI will enable more robust tests of large-scale homogeneity and isotropy, and will allow cross-checking of MG2 and quasar tracer claims with higher quality data. The sheer volume of spectra, nearly 20 million in DR1 alone, with the full survey expected to exceed 40 million, provides unprecedented statistical leverage. Euclid, the European Space Agency mission, released its first survey data on March 19, 2025. ESA highlights deep fields showing large-scale organization of galaxies, with 26 million galaxies in the release and the farthest galaxies at more than 10.5 billion light-years. Euclid is designed for a 6-year survey of approximately 1/3 of the sky, providing uniform wide-field coverage that will strengthen homogeneity and cosmic web mapping. Euclid's space-based platform provides advantages unavailable from the ground: no atmospheric distortion, uniform photometry across the sky, and access to wavelengths blocked by Earth's atmosphere. The combination of optical and near-infrared imaging enables photometric redshift estimation for billions of galaxies. The Vera C. Rubin Observatory released first images on June 23, 2025. Full survey operations are planned for early 2026. Rubin's legacy survey of space and time will generate deep time domain and large-scale structure data relevant to isotropy tests. Rubin's 8.4-meter primary mirror and 3.2 gigapixel camera will image the entire southern sky every few nights for 10 years. The resulting dataset, hundreds of petabytes of imaging data, will enable studies of structure at all accessible scales. The Nancy Grace Roman Space Telescope, NASA reports construction complete in December 2025, with launch targeted as early as fall 2026. Roman's wide-field infrared imaging will strengthen large-scale structure mapping, weak lensing, and geometry constraints. Roman carries a 2.4-meter primary mirror, the same size as Hubble, but with a field of view 100 times larger. This combination of resolution and coverage is specifically designed for cosmological surveys. These surveys will not immediately resolve the disputes. Science rarely works that way. They will provide more data, better systematics control, and independent verification or refutation of current claims. The Big Ring paper explicitly points to DESI spectra as a future improvement, enabling better characterization of MG2 absorbers and cross-checking with spectroscopic galaxy samples. If the giant arc and Big Ring are real physical structures, they should appear in independent surveys with different traces. If they are artifacts of MG2 sparsity or SDSS-specific systematics, they should not. This is how the debate will eventually be resolved. Not by argument, but by data. Independent surveys, multiple traces, consistent or inconsistent results. Let me now address the conceptual and philosophical dimensions, the questions that sit at the edge of what science can answer. Science can describe what happens and how it happens. We can measure distances, calculate densities, map structures, test statistical distributions. We can determine that the CMB is uniform to 1 part in 100,000, that homogeneity transition occurs at approximately 100 megaparsecs, that certain structures exceed theoretical limits if the reported measurements are correct. The question of why the universe has these properties, why it is so close to statistically homogeneous and isotropic, why the initial conditions permitted the structures we observe, why these physical laws and not others sits beyond the reach of telescopes and equations. We can measure the distances, calculate the masses, map the structures. What set all of this in motion and why these laws and not others remains unanswered. This is not a failure of science. Science is a method for understanding the physical world through observation, measurement, and mathematical description. It has been extraordinarily successful. The precision of modern cosmology, ages measured to fractions of a percent, distances measured to light years, densities measured to significant figures, represents a remarkable achievement of human inquiry. Science has boundaries. Questions about ultimate origins, why there is something rather than nothing, why the laws of physics take the form they do, why the initial conditions were set as they were. These are questions science can pose but may not be able to answer. They may require frameworks beyond empirical investigation. Even if lambda CDM fits the data perfectly, the deeper questions remain. Why is there a cosmological constant? Why does it have this particular value? A value so small that it could easily have been zero, yet not zero. Why are the initial perturbations nearly Gaussian and nearly scale invariant? Why is the curvature so close to zero? These are not questions lambda CDM answers. They are questions lambda CDM describes. The fitting of parameters is not the same as understanding of causes. Some physicists appeal to anthropic reasoning. We observe these values because only these values permit observers to exist. Others find this unsatisfying, an explanation that explains everything and therefore explains nothing. The debate continues. And if the anomalies, the ultra-large-scale structures, the Cosmic Dipole, the CMB preferred axes, prove to be real deviations from lambda CDM, the questions multiply. What generates gigaparsec-scale coherence? What breaks isotropy? What physics beyond the standard model is required? Some questions may simply be beyond what science alone can address. This is not a limitation to lament. It is a boundary to acknowledge. Let me now present a summary of the evidence, what we know and what we do not know. This is the forensic summary, the case file as it stands, not conclusions. Assessment. What we know. The cosmological principle is a statistical assumption that enables the FLRW metric and standard cosmological inference. The assumption states that on sufficiently large scales, the universe is statistically homogeneous, the same everywhere in a statistical sense, and statistically isotropic, the same in all directions. This is not a claim about individual structures, but about ensemble properties, averages, variances, correlation functions. Observational tests using galaxy counts in spheres show homogeneity transition at approximately 70 to 100 hours inverse megaparsecs, roughly 100 to 140 megaparsecs. Above this scale, the correlation dimension d sub 2 approaches 3 within tolerance, meaning the distribution becomes consistent with uniformity. The Wigglesy survey excluded fractal behavior at 99.99% confidence on scales of 80 to 300 hours inverse megaparsecs. Theoretical estimates place an upper limit to the homogeneity scale at approximately 260 hours inverse megaparsecs, roughly 370 megaparsecs. This is the scale beyond which lambda CDM does not predict coherent structures to exist. Structures larger than this limit, if they are genuine physical overdensities, would represent a tension with standard cosmology. 3 structures have been reported that exceed this limit. The Huge-LQG at approximately 1,240 megaparsecs longest dimension, the Giant Arc at approximately 1,000 megaparsecs, and the Big Ring at approximately 400 megaparsecs. Each has been published in peer-reviewed journals. Each has sparked debate. The Huge-LQG was found using quasar clustering with a 100 megaparsec linking length. The structure contains 73 quasars at mean redshift Z, approximately 1.27. The reported CHMS departure from random expectations was 3.81 sigma. The estimated overdensity was delta sub Q, approximately 0.40. Critics argue similar structures appear in random Poisson simulations at a rate of approximately 8.5%. Critics argue the linking length is too large, that smaller linking lengths produce structures indistinguishable from random. Critics argue Counts in Spheres analysis shows the DR7QSO catalogue is consistent with homogeneity above approximately 130 hours inverse megaparsecs. The Huge-LQG, by this analysis, does not falsify statistical homogeneity. The Giant Arc was found using Mg2 absorbers at redshift Z, approximately 0.8. The structure spans approximately 1 gigaparsec. The reported significance was method-dependent, 3.0 to 4.8 sigma, depending on statistical test. The estimated overdensity was delta RO over RO, approximately 1.3. Critics argue the Mg2 tracer is sparse and susceptible to pattern-finding artifacts. Critics argue look elsewhere effects, the inflation of significance when searching across many sky positions and redshift slices, may not be adequately controlled. A 2025 preprint frames the Giant Arc as filament or figment, a question requiring verification rather than an established challenge to cosmology. The Big Ring was found using Mg2 absorbers at the same redshift as the Giant Arc, with sky separation of approximately 12 degrees. The diameter is approximately 400 megaparsecs. The reported CHMS departure reached up to 5.2 sigma. Critics apply the same concerns as for the Giant Arc: tracer sparsity, look elsewhere effects, the need for independent verification with different tracers. The proximity of the Big Ring and Giant Arc raises additional questions. Are these independent structures, or are they related? Does their proximity increase or decrease the probability of statistical artifact? The Cosmic Dipole anomaly, a matter-dipole amplitude exceeding kinematic expectations, has been reported at 3 to 5 sigma significance depending on analysis. The direction aligns with the CMB dipole, both point roughly toward Leo. The amplitude is approximately 2 to 3 times larger than predicted from our kinematic motion alone. The 2021 Catwise analysis reported a p-value of approximately 5 times 10 to the negative 7 for rejecting a purely kinematic interpretation. The 2023 DAM analysis reported 5.7 sigma significance for an excess dipole amplitude. The 2025 reassessment with improved systematic modeling reduced the significance to 3.3 to 3.6 sigma, notable but not decisive. If the cosmic dipole anomaly is real, it implies the matter distribution has an intrinsic directional asymmetry beyond what our motion through the CMB rest frame predicts. This would violate statistical isotropy at the largest observable scales. The KBC Void, a local underdensity of approximately 20% out to approximately 300 megaparsecs, is supported by K-band luminosity measurements. Beyond Z approximately 0.07, the K-band luminosity density rises to approximately 1.5 times the local value, suggesting local underdensity if luminosity traces mass. The KBC Void implies we may not live in a fair sample region. Local cosmological measurements, including the Hubble constant, may be biased relative to global values. Some analyses argue the KBC Void could partially explain the Hubble tension. Others argue the effect is too small to account for the full discrepancy. CMB large-angle anomalies, including hemispherical asymmetry and low multipole alignment, are confirmed in the Planck data but not yet decisively attributed to new physics versus statistical flukes or residual systematics. The anomalies exist. Their interpretation is debated. What we do not know, whether the Huge-LQG, giant arc and big ring are physical overdensities or pattern-finding artifacts. The structures exist in the data. The patterns are real in the sense that they appear when you apply the relevant algorithms to the relevant catalogs. Pattern and structure are not synonyms. A pattern can arise from chance alignment. A physical structure requires gravitational or other physical binding. The distinction is essential and often obscured in popular discussions. Finding a pattern is not the same as discovering a structure. The pattern must be shown to exceed what random processes predict. And the threshold for exceeding random predictions depends on method, which is why different analyses reach different conclusions. Whether the cosmic dipole anomaly is cosmological or systematic, the measurements are real. The discrepancy is real. Discrepancies can arise from many sources. Systematic errors in catalog construction, stellar contamination, flux calibration, sky coverage gaps. Inadequate modeling of local structure effects. Statistical flukes in finite samples. Each must be ruled out before concluding that the cosmos itself is anisotropic. The trajectory of the literature suggests progress. Early analyses reported higher significance. Later analyses with better systematic modeling report lower significance. This is normal scientific refinement. Whether the significance will ultimately converge to decisive detection, decisive non-detection, or persistent ambiguity remains to be seen. Whether local non-avereness, the KBC Void, significantly biases cosmological parameter inference. The void exists in the sense that K-band luminosity density measurements show local underdensity. The magnitude of the bias on parameters like h sub 0 depends on modeling assumptions, how underdensity translates to peculiar velocity, how peculiar velocity affects redshift distance inference, how these effects propagate to parameter fits. Different modeling approaches yield different conclusions. Some find the KBC Void could ease the Hubble tension significantly. Others find the effect is modest. The debate reflects genuine uncertainty in the modeling, not just disagreement about interpretation. Whether the CMB anomalies have a common origin or are independent fluctuations. The hemispherical asymmetry and low multipole alignment could be manifestations of a single underlying cause, some early universe process that imprinted directional dependence. Or they could be independent statistical flukes that happen to appear in the same dataset. Without a theoretical framework that predicts both anomalies, distinguishing these possibilities is difficult. Whether any of these signals, individually or collectively, constitute decisive evidence against the cosmological principle. This is the central question, and it remains open. The anomalies exist. Their interpretation is contested. The cosmological principle is under test, but not yet refuted. This is the current state of knowledge. Not resolution. Assessment. When I first understood this, the conditional nature of our cosmological framework, the anomalies that persist without resolution, the methodological disputes that cannot be settled by argument alone, I had to stop. Just stop and sit with what it meant. We have built an extraordinarily precise model of cosmic history, the age of the universe to within 23 million years, the matter density to within a few percent, the geometry to within measurement precision of flat. And yet the model rests on an assumption, statistical homogeneity and isotropy, that remains challenged by patterns we can see but cannot definitively interpret. The homogeneity scale itself is a statistical statement. The universe does not become perfectly uniform at 100 megaparsecs. It becomes statistically consistent with uniformity. The variance shrinks. The correlation dimension approaches 3. Structures remain. The cosmic web, filaments and voids and walls persists at all scales we can observe. The question is whether the statistics of that web match predictions. And in that question, everything depends on method. How you define a structure, which traces you use, which linking length, which null model, which significance estimator. The same data can produce different answers depending on these choices. This is not a weakness of science. It is a feature. The methodology must be scrutinized. The choices must be justified. The results must be replicated. And when independent methods disagree, we must understand why. The Huge-LQG was reported in 2013. 12 years of debate followed. The giant arc in 2022. The Big Ring in 2024. Each claim sparked counter-analyses. Each counter-analysis sparked responses. The debate continues. Let me trace this timeline more precisely because the history illuminates the science. In 1996, a review paper explicitly used the phrase "end of greatness" to describe the empirical scale where survey volumes become fair samples rather than being dominated by individual massive structures. This was the state of knowledge before modern precision surveys. Homogeneity was expected on theoretical grounds, but not yet rigorously measured. In 2004 and 2005, David Hogg and collaborators demonstrated cosmic homogeneity using luminous red galaxies from SDSS at Z approximately 0.3. This was among the first direct confirmations that counts in spheres scale as R, cubed above approximately 70 H inverse megaparsecs. The cosmological principle had empirical support. In 2010, Yadav, Bagla, and Kandai published theoretical estimates for the homogeneity scale upper limit, approximately 260 H-inverse megaparsecs under idealized lambda CDM assumptions. This provided a theoretical benchmark. Structures larger than this limit should not exist. In 2012, Scrimger and collaborators published the Wiggle-Z homogeneity analysis, the most rigorous counts in spheres test to date. They confirmed homogeneity transition at 70 to 81 hours inverse megaparsecs and excluded fractal behavior at 99.99% confidence. The cosmological principle was on firm empirical footing. Then, in 2013, the Huge-LQG was reported, a structure apparently exceeding the theoretical limit by a factor of 3. The cosmological community responded with both interest and skepticism. Nadathur's critique came within months. The counts in spheres test showed DR7 QSO was homogeneous. Poisson simulations produced similar structures at 8.5% probability. The Huge-LQG might be artifact, not anomaly. In 2013 also, Keenan, Barger, and Cowie published evidence for the KBC Void, local underdensity on a 300 megaparsec scale. This added another potential challenge. Not just distant structures exceeding limits, but local non-avereness affecting all our measurements. In 2015, Park and collaborators showed that DR7 QSO structures at 70 hours inverse megaparsec linking length were statistically indistinguishable from random. The significance of large quasar groups depended critically on linking length choice. In 2018 and 2020, the Planck collaboration released final cosmological parameters and isotropy/statistics analyses. The CMB remained consistent with lambda CDM, but anomalies were confirmed, including hemispherical asymmetry and low multipole alignment. In 2021, Seacrest and collaborators reported the cat-wise Cosmic Dipole anomaly matter dipole amplitude more than twice the kinematic expectation at 4.9 sigma. If confirmed, this would be the clearest violation of isotropy. In 2022, the giant arc was reported, a gigaparsec scale structure in MG2 absorbers. Different tracer, different method, but similar tension with homogeneity limits. In 2024, the Big Ring was reported, another large structure near the giant arc, raising questions about physical connection versus chance proximity. In 2025, reassessments of the Cosmic Dipole with improved systematic modeling reduced significance from 5 sigma to 3 to 4 sigma. Still notable, not decisive. Also in 2025, Euclid and Rubin began releasing data. Roman completed construction. The next generation of surveys was coming online, surveys that would provide the statistical power to resolve these debates. This is how science works when evidence is partial and interpretation is contested. Not rapid resolution, slow accumulation. Eventually, the evidence will become clear enough, one direction or the other. For now, we wait. We collect more data. We refine our methods. We argue about linking lengths and look elsewhere effects and tracer sparsity. And the structures sit in the catalogues, patterns we named, patterns we debate, patterns whose reality remains uncertain. Let me now discuss what would change if these anomalies were confirmed? This is a conditional analysis, exploring the consequences of hypotheticals. The anomalies are not confirmed. Understanding what confirmation would mean helps clarify the stakes. If the ultra-large-scale structures, the Huge-LQG, the giant arc, the Big Ring, were demonstrated to be genuine physical overdensities inconsistent with lambda CDM, the implications would cascade. First, the cosmological principle would require modification. Not abandonment, the CMB remains strikingly uniform, but refinement. Perhaps homogeneity holds at the very largest scales, but breaks down at intermediate scales. Perhaps isotropy holds on average, but with larger fluctuations than lambda CDM predicts. The precise nature of the modification would depend on the pattern of violations. Consider the scales involved. The CMB probes the universe at Z, approximately 1090, when it was only 380,000 years old and approximately 1,000 times smaller than today. At that epoch, the co-moving horizon, the maximum distance over which causal contact had occurred, was approximately 300 megaparsecs in present-day units. Structures larger than this could not have been in causal contact before the CMB was released. If gigaparsec scale structures exist today, they must trace back to correlations established before the CMB epoch, during or before inflation. Standard inflation produces correlations on all scales, but with decreasing amplitude at larger scales. Gigaparsec scale coherent overdensities would require more power at large scales than standard inflation predicts. Second, the FLRW metric would become an approximation in a more precise sense. The equations that assume perfect homogeneity would need perturbative corrections. The back reaction debate, whether inhomogeneities affect the averaged expansion, would gain observational urgency. Back reaction is a technical term for a conceptually simple idea. When you average over an inhomogeneous distribution, the average of a function is not the same as the function of the average. Applied to general relativity, this means that averaging the Einstein equations over an inhomogeneous spacetime does not yield the same result as solving the equations for a homogeneous spacetime with average density. The question is, how large is this difference? Some researchers argue it is negligible for realistic inhomogeneities. Others argue it could contribute to cosmic acceleration without requiring dark energy. The debate is unresolved, but confirmed large-scale inhomogeneities would intensify it. Third, initial conditions would require explanation. Gigaparsec scale coherence cannot arise from standard structure formation in a 13.8 billion year universe. The light crossing time exceeds the available time. Something in the early universe, during or before inflation, would have to seed these correlations. This connects to fundamental questions about the initial state of the universe. Why were the initial perturbations what they were? Why nearly Gaussian? Why nearly scale invariant? These questions are not answered by lambda CDM. They are inputs to lambda CDM. Confirmed anomalies would add to the list of unexplained initial condition features. Fourth, alternative cosmologies would gain attention. Anisotropic cosmologies, Bianchi models that allow homogeneous but anisotropic expansion, non-trivial topology, finite fundamental domains that could create apparent large-scale correlations. cosmic strings or other topological defects. These would move from theoretical curiosities to observational necessities. If the Cosmic Dipole anomaly were confirmed, if the matter rest frame genuinely differs from the CMB rest frame beyond kinematic expectations, the implications would be equally significant. The universe would have an intrinsic direction. The assumption of statistical isotropy would fail. Cosmological parameter inference would need to account for anisotropic effects. The matter-dipole anomaly, if real, would be particularly troubling because it would indicate a fundamental difference between the early universe, as probed by the CMB, and the late universe, as probed by matter distributions. The CMB dipole is kinematic. It reflects our motion. The matter dipole should also be kinematic, reflecting the same motion. If the amplitudes differ, something is wrong with our understanding. Several possibilities exist. First, the matter catalogues might have uncontrolled systematic errors, stellar contamination, flux calibration issues, incomplete sky coverage that inflate the apparent dipole. Second, the kinematic prediction might be incomplete. Perhaps relativistic effects or nonlinear clustering contribute more than expected. Third, the universe might genuinely be anisotropic at late times, with matter distributed preferentially in one direction. The third possibility is the most dramatic. It would require fundamental revision of cosmological assumptions. It would imply that the FLRW metric, which assumes isotropy, is inadequate for describing the actual universe. Anisotropic cosmological models exist. The Bianchi classification describes all possible homogeneous but anisotropic spacetimes. These models have been studied theoretically and constrained against CMB observations. Planck data allow only limited room for anisotropic expansion. The CMB is too uniform to accommodate large deviations. The CMB probes the early universe. Late-time anisotropy that develops after the CMB was released would be a different phenomenon. Non-trivial cosmic topology offers another possibility. In standard cosmology, space is simply connected. Any loop can be contracted to a point. Mathematically, space could have a more complex topology, a torus-like structure, where traveling far enough in one direction brings you back to your starting point. Such topologies could create apparent large-scale correlations by making the fundamental domain of the universe finite. The Planck collaboration searched for evidence of non-trivial topology using matched circle searches in the CMB. They found no evidence for compact topologies smaller than certain limits. Larger fundamental domains remain possible. If the universe has non-trivial topology with a fundamental domain of order, a few gigaparsecs, structures at that scale could show unexpected correlations. The cosmic string hypothesis, mentioned in the Big Ring paper, represents yet another possibility. Cosmic strings are theoretical one-dimensional topological defects that could form during phase transitions in the early universe. If they exist, they would seed distinctive patterns in the matter distribution, linear features, possibly ring-like structures if the string has the right geometry. CMB observations and gravitational lensing searches constrain the contribution of cosmic strings to structure formation. No definitive detection has been made. The constraints are model-dependent, and some cosmic string scenarios remain viable. These alternative explanations illustrate an important point. Even if the ultra-large-scale structures are confirmed as real physical overdensities, explaining them would be challenging. Standard lambda CDM does not predict them. Alternative physics, inflation modifications, cosmic strings, non-trivial topology would be required, and each alternative brings its own theoretical and observational challenges. If the KBC Void were confirmed as a significant bias on local measurements, the Hubble tension would have a partial explanation. But the deeper question would arise: why are we located in an unusual region? Is this chance? Is it selection effect? Is our location correlated with something else? None of this is confirmed. These are conditionals. They illustrate the stakes. The cosmological principle is not a decorative assumption. It is load-bearing. Remove it, and the structure requires redesign. Let me now offer perspective, not hope, not despair, but placement. We measure the universe with instruments that took centuries to develop. The conceptual framework, that the universe can be measured at all, that physical laws apply uniformly across cosmic distances, that mathematics describes reality, this framework emerged from millennia of human inquiry. The instruments themselves represent generations of engineering. The Sloan Digital Sky Survey, 2.5 meters of aperture, 30 years of technology development, billions of observations. The telescope sits on a mountain in New Mexico, rotating through the night, collecting photons that left their sources billions of years ago. Each photon that strikes the detector has traveled for longer than complex life has existed on Earth, and we catch it, measure it, catalog it. The Planck satellite cryogenic detectors at 0.1 Kelvin, 1.5 million kilometers from Earth at the L2 Lagrange point, mapping the sky at 9 frequencies for 4 years. The detectors were cooled to near absolute zero to reduce thermal noise. The satellite drifted in space, far from Earth's interference, scanning the sky in great circles. The data it returned, terabytes of measurements, encode the state of the universe when it was 380,000 years old, seen through a filter of 13.8 billion years of cosmic expansion. DESI, 5,000 robotic fiber positioners, each able to target a different galaxy or quasar simultaneously, collecting millions of spectra. The fibers must be positioned with micrometer precision. Each night, the system reconfigures thousands of times, pointing at new targets, gathering light from objects across the sky. The resulting spectra reveal redshifts, and from redshifts, distances, and from distances, structure. With these instruments, we map patterns in light that left its sources billions of years ago. The giant arc at redshift 0.8, the light we observe left those MG2 absorbing halos approximately 7 billion years ago. The Huge-LQG at redshift 1.27, the light left approximately 8.8 billion years ago. We are not observing the universe as it is. We are observing the universe as it was. This is a limitation. The universe we see is a composite of different epochs, nearby objects as they are now, or nearly so, distant objects as they were long ago. We cannot observe the giant arc now. We can only observe the light that left it 7 billion years ago. Whether the structure still exists, whether it has changed, whether our interpretation is correct, we cannot directly check. And from these ancient photons, we attempt to infer whether the universe is statistically uniform, whether patterns we detect are real or artifacts, whether our foundational assumptions hold. The speed of light constrains what we can know. The giant arc spans 3.26 billion light-years. Light cannot cross it in less than 3.26 billion years. If it is a coherent structure, if the overdensity is physically connected, then something in the early universe created that coherence. We cannot observe the structure directly. We can only observe its traces, absorption features in quasar spectra, themselves billions of light-years away. We are trapped, not in the structure, but in our observational position. We cannot move to see from another angle. We cannot wait for the light to arrive from the other side. We have one vantage point, one moment in cosmic time, one set of photons that happen to have reached us. From that position, we infer everything. The observable universe spans approximately 93 billion light-years in diameter, the co-moving distance to the most distant photons we can detect. Beyond this horizon, light has not had time to reach us since the Big Bang. We do not know what lies beyond. We cannot know. The horizon is not a physical barrier, but an informational one, a limit to what can be observed from here, now. Within this horizon, we see approximately 200 billion galaxies, each containing hundreds of billions of stars. We see the cosmic web, filaments and voids spanning hundreds of megaparsecs. We see the CMB, the thermal relic of the early universe, uniform to 1 part in 100,000. And we see patterns that may or may not challenge our assumptions. The cosmological principle remains the working hypothesis. The FLRW metric remains the framework. The lambda CDM model remains the best fit to the data. The anomalies persist, the structures too large, the dipole too strong, the axes too aligned. They may be noise, they may be systematics, they may be hints of something else. We cannot know yet. The data does not decide. And we build more instruments. Euclid maps the sky, Rubin surveys the south, Deci collects spectra, Roman prepares for launch. Each survey brings more data, better systematics control, new tests. The CMB remains our most powerful probe of early universe conditions. The temperature of the CMB, approximately 2.725 Kelvin, measured by the COBE satellite's FIRUS instrument with extraordinary precision, represents the thermal state of the universe when it was 380,000 years old. The uniformity of this temperature, 1 part in 100,000 across the sky, after removing the kinematic dipole, is direct evidence for early universe homogeneity. Any fundamental violation of the cosmological principle would need to either be absent at early times, emerging only after the CMB was released, or be subtle enough to hide within the CMB's tiny fluctuations. This constrains the possible explanations for the ultra-large-scale structure anomalies. If they are real physical features, they must have formed from processes operating after CMB release, or from initial conditions so subtle that the CMB does not clearly reveal them. The cosmological principle, statistical homogeneity and isotropy, is either true or false at the scales and precision we can probe. We do not know which. We are working to find out. The ultra-large-scale structures, the Huge-LQG, the giant arc, the Big Ring, either challenge the cosmological principle or they do not. The Cosmic Dipole anomaly either indicates genuine anisotropy or it does not. The KBC Void either biases our inferences or it does not. The answers will come from data, not from hope or assumption. What we have for now is the evidence. 3 structures spanning billions of light years. A matter dipole larger than expected. A local void possibly biasing local measurements. CMB anomalies that refuse to disappear but refuse to be conclusive. 1,240 megaparsecs, 4.04 billion light years. A structure whose light cross in time is 30% of cosmic history. If it is real, it is larger than physics, as we currently understand physics allows. If it is real, the cosmological principle underwrites our equations. The FLRW metric enables our calculations. The Friedmann equations describe expansion under these assumptions. Planck measured the CMB, SDSS catalogued the quasars. DESI is collecting spectra. Euclid has begun its survey. We map, we measure, we compute, we test. And the structures sit in the data, patterns that may be real, patterns that may be noise, patterns that we found because we looked. The giant arc, the big ring, the Huge-LQG. Names we gave to arrangements of light. The universe does not confirm or deny. The data accumulates. The debate continues. The homogeneity scale, 370 megaparsecs by theoretical estimate, 100 megaparsecs by empirical transition. The Huge-LQG exceeds both by a factor of 3 or more. The giant arc exceeds both by a factor of 2 or more. The big ring exceeds the empirical transition by a factor of 4. If these patterns are physical structures, we are trapped in a universe larger than physics allows. Not trapped physically, trapped epistemically. Our models do not predict what we observe. Our assumptions do not hold where we test them. If these patterns are artifacts, we are trapped in a different sense, in the limitations of sparse data, algorithm choices, and statistical inference. Patterns that appear significant but dissolve under scrutiny. Either way, we are trapped by the limits of what we can measure, by the constraints of what we can infer, by the boundaries of the observable universe itself. The cosmological principle, the FLRW metric, statistical homogeneity and isotropy. These remain the framework. The Huge-LQG, the giant arc, the big ring, the Cosmic Dipole anomaly, the KBC Void. These remain the challenges. We do not know the resolution. We are working toward it. And here we are, brief, small, mapping billion light-year patterns with instruments we barely understand. Uncertain whether we are seeing structure or illusion. Uncertain whether the homogeneity we assume is real or a useful fiction. The quasars that comprise the Huge-LQG are supermassive black holes at the centers of distant galaxies, each one millions to billions of solar masses, each one accreting matter and emitting radiation across the electromagnetic spectrum. They are among the brightest objects in the universe. We detect them as points of light, measure their spectra, determine their redshifts. And then we ask, are they clustered? Do they form a pattern? Is that pattern significant? The MG2 absorbers that trace the giant arc are not the galaxies themselves, but the gas in their halos, magnesium atoms absorbing specific wavelengths of light from background quasars. We cannot see the galaxies directly at this distance, and with this method, we see only the shadow they cast on the light of more distant objects. And from those shadows, we infer structure. This is the nature of observational cosmology. We do not see the universe directly. We see photons that have traveled for billions of years, carrying information about objects that may no longer exist as they were. We construct models. We test predictions. We argue about significance and systematics. The evidence remains open. The cosmological principle remains under test. The ultra-large-scale structures remain contested. We have the data. We do not yet have the answer. The journey of scientific understanding is never complete. Each answer generates new questions. Each measurement reveals new uncertainties. The cosmological principle has survived a century of testing. Whether it will survive the next decade, whether the anomalies will sharpen into refutation or fade into noise, remains to be seen. The surveys continue. Euclid maps the cosmic web. Rubin images the southern sky. DESI collects spectra. Roman will launch and add its data. Each year brings more observations, more analyses, more refinement. Perhaps the anomalies will fade, revealed as artifacts of sparse data, marginal statistics, and human pattern-seeking. Perhaps they will sharpen, confirmed by independent methods, different traces, larger samples. Perhaps they will persist in ambiguity, significant enough to notice, not significant enough to conclude. We do not know which outcome awaits. We only know that the question matters. The cosmological principle is not an arbitrary assumption. It is the foundation of modern cosmology, the enabling principle that allows us to write equations, fit parameters, make predictions. If it fails, we must rebuild from scratch. If it holds, we have confirmed one of the deepest assumptions about reality, that the universe, for all its apparent complexity, is fundamentally simple at large scales. The same laws, the same statistics, everywhere. We are testing this. We have not finished. And the structures sit in the catalogues, patterns we named, patterns we debate, patterns whose reality remains uncertain. The huge, large quasar group, the giant arc, the big ring, names for arrangements of light from objects that are themselves unimaginably distant. The universe does not care about our debates. The photons arrive whether we understand them or not. The structures, if they are structures, exist independently of our interpretation. The cosmological principle, if it holds, holds whether we can prove it or not. We are the ones who care. We are the ones who measure and argue and wonder. And here we are. Good night.